last class we have studied about the vibration of continuous system, in which we have taken the Euler-Bernoulli beam and we have found the mode shapes for fixed beam, simply supported beam and cantilever beams. So, in those cases we have seen the vibration of the beam can be written in terms of this Euler-Bernoulli equation, that is del square u del square w by del t square plus so rho into EI del fourth w by del x fourth equal to 0. So, in this case this is the governing equation, that is the Euler-Bernoulli equation. Here rho is the mass per unit length, EI is the flexural rigidity of the system, W is the deflection. So, if this is a cantilever beam, so in this cantilever beam, so the vibration will takes place in the transverse direction. So, this transverse direction deflection I have taken it equal to W. So, this W is a function of x and t, and so we have found this W, we have written it in terms of phi x and q t. So, phi x is the mode shape and q t is the time modulation of the system. So, for simply supported case we have seen the mode shape in this form. So, I have shown the mode shape, this is the mode shape for the first mode, this is for the second mode, this is for the third mode and this one is for the fourth mode. So, you can observe that there is a node at L by 2 or at the middle of this in case of a simply supported beam when it is vibrating with first mode. So, in case of first mode there is no node, and in case of second mode there is a single node formed here. So, this is the beam. So, in the first mode this is the vibration of the system, and the second mode this is the vibration of the system. So, this is along the length of the beam, and here you can find at this point there is no vibration. So, this point has a node, this point is the nodal point. So, initially for the second third mode also this is the line, and you have this and this point will have 0 vibration. Similarly, in case of fourth mode these are the points where there will be 0 vibration. So, you can see the simulation of this by using, you can write a simple program in MATLAB to find this thing. So, in the program you can write the expression for this phi x. So, already you have derived this phi x equal to a sin n pi x by L, and this omega equal to beta square L square into root over E I by rho L fourth. And in case of simply supported beam you have found this beta L value equal to n pi by L. So, using this expression you can write a simple code in MATLAB to simulate the vibrations of the simply supported beam. So, in this case you can write this vibration W x t will be equal to phi x into q t. So, q t is nothing but this is the C1 sin omega t plus C2 sin omega t. So, where C1 and C2 depends on the initial conditions. So, this W x t you can write equal to a. So, for nth mode you can write this W n x t equal to a n sin n pi x by L into C1 sin omega t plus C2 sin omega t. So, this a n term is arbitrary. So, you can normalize this term to get the actual value of a 1. So, let me show the simulation for this. So, you can write this expression and you can simulate this value. So, let us do the simulation for this case. So, in this case of a simply supported beam, so this is for a simply supported beam, the program is written for a simply supported beam. So, in this case you can see here in this program I asked for the number of mode, so whether it is first, second or third, fourth, and so the beta L value for nth mode is known to us. So for beta L equal to n pi, so this beta L for nth mode will be n pi, and we can write taking this ei by rho L fourth equal to 1, you can find this w function. This w is written in terms of yf, this is sin omega t, and this is the mode shape C1 sin beta x. So to simulate this thing, so you just run this and check. So for different modes you can find, for different mode let us find it for the first mode. So for the first mode, so if you give the time, let us simulate it for 10 seconds, and you can see for the simply supported case, so the vibration takes place like this. So at these 2 points the vibration are 0, so at these 2 points it is supported. So similarly we can find for the second mode. So for the second mode, you can find it. So let us take for the second mode, and you can observe that so for the second mode you can find, so let us run it for this. So in case of second mode you can observe that at this point, at point 5 there is no vibration of the beam. So there is no vibration of the beam at L equal to 0.5 in case of the second mode, and similarly you can find for the third mode. So for the third mode case, for this case let us see for the third mode. So in this case I am writing it for third. So if you simulate it for, you can see clearly, you can visualize that there are 2 nodes present in this case. So at these 2 nodes there is no vibration, and the beam vibrates in sin n pi x by L. Similarly you can simulate it for fourth mode and other modes also. So let us see the simulation for the case of a cantilever beam. So in case of a cantilever beam you can find the vibration. So for the first mode, let us check for the first mode. So in case of the first mode, so you can see that the free end is moving up and down, and there is maximum deflection in the free end, and in the fixed end you can observe up to certain extent there is no vibration of the free end. So up to certain extent the vibration in case of free fixed end, it is slope will be equal to 0. Similarly for the second mode, so if you want to find for the second mode in case of a simply supported beam, so let us find for the second mode. So in this case you can so in this case you can observe that the beam is vibrating. So there is a node formation here, and you can similarly simulate for the third and fourth mode in this case. So, in case of third mode you can observe there are 2 nodes present in case of third mode of vibration. So, in that case so you can clearly observe there are 2 nodes, one node is here and other node is here in case of third mode of vibration in case of a cantilever beam, and in the fixed end you can clearly observe the slope is 0 and displacements are also 0. So, to see the fourth mode, so in that case also you can find, so in case of fourth mode so clearly you can observe 3 nodes are formed in this beam in the cantilever beam. Similarly, for higher modes n minus 1 number of nodes you can find, and the free end will vibrate with a maximum, and the fixed end there is 0 deflection and the slope is 0 also in this case. So, in case of a cantilever beam you can observe that first frequency correspond to beta L, that is equal to 1.875, the second modal characteristic function that is beta L2 that is equal to 4.694, and for the third mode it is equal to 7.853, and fourth mode 10.996, and fifth mode it is equal to 14.137. So, taking those value, so you can simulate for different modes and you can find the mode shapes and the response of the system. So, in case of cantilever beam already you have seen that the vibration, these are the mode shapes, this is for the first mode and this is for the second mode, and in the second mode a node is formed at this position. In case of third mode there are 2 nodes, and in case of fourth mode there are 3 nodes present in this beam. So, in these cases you have found that for nth mode there will be n minus 1 nodes, that is at n minus 1 points on the beam there will be no vibration. In case of fixed beam also if you find, so these are the mode shapes. So, this is a Euler Bernoulli beam. So, in this case both the ends are fixed and slopes are 0 here, and in case of second mode you can see there is 1 node. In case of third mode there is 2 nodes, and in this case you have 3 nodes present. So, the systems represented by wave equations are, so we have studied about 3 systems. In the first systems we have studied about the string. So, the taut string, so in this case the strings in tension, so the vibration of the string in tension and the longitudinal vibration of beam, and the torsional vibration of rod. So, these 3 systems you can write the equation motion for these three systems by using this wave equation, that is del square u by del t square equal to c square del square u by del x square. So, in these cases, so the c, so in case of a taut string, c equal to T by rho, where rho is the mass per unit length. So, mass per unit length, and in case of this longitudinal vibration of rod, c equal to root over E by rho, and in case of torsional vibration of rod it is equal to G by J. So, here in case of, so in all these cases you can check that the C represent a velocity term, and already you have solved this wave equation and you have found the response u x t can be written in this form, u x t equal to phi x into q t, where this phi x you have written as a cos omega by c x plus b sin omega by c x, and q t you have written in this form, q t equal to c 1 sin omega t plus c 2 cos omega t. So, for different boundary conditions today we will find the mode shapes for these systems. So, let us first take the system of a string. For this case, for the fixed spring we have already found the mode shapes, and in this case when it is fixed, as both ends are fixed in this string, so the displacements are 0. So, phi, so your u 0 t equal to 0 and u l t also equal to 0. So, as u 0 t equal to 0 and u l t equal to 0 for all time, so you can write this phi 0 equal to 0 and phi l equal to 0. So, when phi 0 equal to 0, in that case a cos omega by c x plus b sin omega by c x equal to, so at x equal to 0 this will be equal to 0. So, this is expression for phi x. So, I can write this phi 0 equal to, so this is equal to a into 1 plus b into 0 implies this a equal to 0. Similarly, phi l will be, as a equal to 0, phi x becomes b sin omega by c x. Now, substituting x equal to l, so you can write this is equal to b sin omega by c l equal to 0. So, as omega sin omega by c l equal to 0, so this equal to sin, so b will not be equal to 0, as b, when b will be equal to 0, phi x will becomes 0. So, the case will be a trivial solution of the system. So, as we are interested for the non-trivial solution of the system, that is when the beam or when the string is vibrating, as we are interested to see the vibration of the string. So, in that case we should, b will not be equal to 0. So, as b not equal to 0, so our frequency equation will be sin omega by c l equal to 0. So, as sin omega by c l equal to 0, so this omega l by c will be equal to n pi, or omega will be equal to n pi by l into c. So, for this case of string you found this as root over T by m or T by rho. So, rho is the mass per unit length and T is the tension in the string. So, if this is the string and this is the tension in the string. So, this omega, so as you have seen this is n, so it depends on the number of modes. So, as you will go on increasing this n, so you will have different values of omega. So, this can be written as the nth modal frequency of the system. So, the nth modal frequency of the system can be written as n pi by l into root over T by rho. So, the modal or the mode shape of the nth frequency, so phi n x can be written as, so phi x equal to a cos omega by c. So, already you have seen this a equal to 0. So, phi x equal to b sin omega by c x. So, for nth mode I can write this equal to b n sin n pi x by l. So, phi n equal to b n sin n pi x by l. So, for different modes, as this phi n equal to b n sin n pi x by l. So, for different mode this b n be different. So, for first mode this is B1, second mode B2 and nth mode it is Bn. So, this is similar to the mode shapes you obtained in case of multi degrees of freedom systems. So, in that case you have normalized that mode shapes and you have found the normalized mode shape of that system. You can write this nth mode amplitude equal to 0, or you can write this phi nx rho x into phi nx dx. So, 0 to L. So, this should be equal to 1. So, you can normalize this mode shape by using this formula, similar to the things you have done in case of the multi degree of freedom system, where you have taken the weighted modal matrix and found this. So, let P the weighted modal matrix. So, you have found this thing P weighted modal matrix transpose MP. So, you have seen this equal to, or you have found this equal to I. So, in this case you have got the diagonal terms 1. So, similarly by making this normalization you are making the mode shapes. So, you can normalize the mode shapes of the nth mode. So, to normalize this thing, so you can write this phi nx into rho x into phi nx dx equal to 1. So, for the string, this mass per unit length I can take it constant. So, this is equal to 1, this is equal to rho. So, this mass per unit length equal to rho, I can take it out. Similarly, substituting this equation in the second equation, this first equation in the second equation, I can write rho into b n square integral 0 to L sin square n pi x by L dx equal to 0 equal to 1. So, when I am normalizing this thing, so I can write rho b n square integration 0 to L sin square n pi x by L dx equal to 1. Already you know the sin square theta, you can write in this form half 1 minus cos 2 theta. So, this integration, previous integration, so this integration you can find by writing this way. So, rho beta n rho b n square. So, integration the sin square n pi x, you can write this is equal to 0 to L 1 minus cos 2 n pi x by L dx. So, this integration will become rho b n square. So, this is x minus this cos integration will be sin. So, this is sin 2 n pi x by L divided by, so you can divide this by 2 n pi by L. So, this is from 0 to L. So, this integration you can find that this is equal to, so you can substitute x equal to L. So, there is a half term here, as we have sin square theta equal to half 1 minus cos 2 theta. So, I can have this half term. So, this is half rho b n square. So, the sin 2 pi n x for value of sin 2 pi n x by L for x equal to L, this is equal to sin 2 n pi. So, this sin 2 n pi equal to 0. Similarly, when x equal to 0, this is sin 0. So, sin 0 equal to 0. So, you will have this term only equal to half rho b n square L. So, this is equal to, so you can substitute this and you can write this equal to 1. So, you can write this b n square. So, b n square will becomes equal to 2. So, this is equal to 2 by rho L, or b n you can write equal to root over 2 by rho L. So, the normalized mode shape you can write as b n equal to root over 2 by rho L sin n pi x by L. So, this is the normalized mode shape or eigenfunction of the string. So, now you can show that these eigenfunctions or these mode shapes are orthogonal. To show mode shapes are orthogonal, so we can to show these mode shapes are orthogonal with respect to this mass matrix. In case of multi degree of freedom system you have seen. So, in this case also you can show that the mode shapes are orthogonal by writing these things. So, 0 to L rho phi r. So, let us take the rth mode and this phi r into rho x into phi s mode. Let us take r and s mode. So, we should show that if the mode shapes are orthogonal, so this integration should be equal to delta r s, where delta r s is the Kronecker delta term. So, delta r s equal to, so this will be equal to 1 when r equal to s and it will be equal to 0 when r not equal to s. So, if they satisfy this equation, then we can show that or we can tell that the systems are or these mode shapes are orthogonal. So, to prove this thing, so already we have found the mode shape for the nth mode. So, phi n x equal to root over 2 by L sin n pi x by L. So, by substituting this expression in this expression, so we can show that. So, when r not equal to s, so this becomes 0 to L. For phi r I can write this is equal to b r sin n pi or r pi x sin r pi x by L into rho x into, for s mode I can write in this form sin s pi x by L dx. So, I can take this rho x constant by taking rho x constant equal to rho. So, this becomes 0 to L, and for this b r I can write this equal to, already you have found this b n, it is equal to root 2 by rho L. So, 2 by rho L I can put it here. So, this becomes, so you obtain this b n equal to 2 by rho L. So, you can substitute that root over 2 by rho L and you can find. So, this will becomes 2 by rho L root over into again another 2 by rho L for this b s. So, you will have sin r pi x by L into sin s pi x by L dx. So, you know the integration or you know this term sin r pi x by L into sin s pi x by L can be written, or you know the term sin alpha into sin beta. Sin alpha into sin beta can be written as half cos alpha minus beta minus cos alpha plus beta. So, if you substitute this thing sin for the sin alpha into sin beta, so you can find for this from this equation rho into 2 by rho L integration 0 to L, and another half will come here. So, this is half. So, this is cos alpha minus beta. So, for this alpha and beta you can write this as r minus s into pi by L into x minus cos r. So, this is r plus x into pi by L into x into dx. So, you have reduced this product of sine terms in terms of cos terms. So, this becomes, so you can divide this 2 and rho got cancelled. So, this becomes, this is equal to 1 by L integration 0 to L cos r minus s by L into pi x minus cos r plus s by L into phi x dx. So, this integration becomes 1 by L. So, for this cos you can write this is integration is sin. So, this is sin r minus s into pi by L x by this is r minus s pi by L minus similarly this becomes sin r plus s by L pi x by r plus s by L into pi. So, this is from 0 to 1. So, you can see that these terms at x equal to L and x equal to 0 it vanishes and this becomes 0. So, when r not equal to s, so you have checked that this integral will be equal to 0, and when r equal to s, so this term you can write this as b r square sin square. So, when r equal to x, so your integration term becomes b r square sin square. So, rho into sin square r pi x by L dx. So, already you have integrated this thing in case of r equal to n, and that integration becomes equal to, so this integration equal to L by 2 you have seen, and the total integration will be equal to 1. So, you have observed that this is equal to 1, and so you can prove that when r equal to s, so when r equal to s, so this integration become 1, and when r not equal to s this becomes 0. So, this proves the orthogonality principle of this mode shapes. So, the mode shapes are orthogonal to each other. So, the mode shapes are orthogonal to each other, that means, so when r not equal to s, so the mode shapes this phi r s into phi s x, phi r x into phi s x equal to 0 when r not equal to s, and when r equal to s 0 to L. So, that case it becomes phi square x dx. So, this will becomes 1. So, this proves the orthogonality property of the mode shapes. Similarly, if you recall this P weighted modal matrix K P, you have checked that this will becomes the eigenfunction, eigenvalues of the system. So, using this weighted modal matrix, this is the stiffness matrix and this is the weighted modal matrix. So, P weighted modal matrix transpose, this is stiffness matrix and this is P matrix for a multi degree of freedom system. So, this becomes equal to lambda, that is the eigenvalue of the system. Similarly, in this case also you can prove that, or you can show that this integration 0 to L rho, so integration 0 to L, so this t phi r x by dx into d phi s x by dx. So, this will be equal to omega r square delta r s, where omega r is the rth mode frequency and omega r square is equivalent to the eigenvalue of the system. So, in this case we will prove this thing. So, already we got the expression for phi x. So, phi r x is the d phi r by dx is the derivative of phi x. So, you can write this thing, this equation in this form. So, this will becomes t into, so by using the normalized mode I can write this as t into 2 by rho L pi r by L into s pi by L integration 0 to L cos r pi x by L into cos s pi x by L dx. So, this thing can be written equal to, so this is, so this integration you can find this equal to L by 2 delta R s. So, this is equal to L by 2 delta R s, that means when r equal to s, this value equal to 0, and when r equal to 0, this value becomes delta R s equal to 1, and when r not equal to s, delta R s equal to 0. So, from this, when r equal to s, you can find this value equal to 2 by rho L into pi square r s by L square. So, this is pi square r L by, so 2 pi square r s by rho L cube. So, this thing can be written as rho L cube into L by 2. So, this becomes pi square. So, this as r equal to s, so it can be written as pi square r square. So, this r into s equal to r square pi square r square by rho L square into t. So, as omega r, already you know this is equal to omega r equal to n pi by L into root over t by m. So, this omega n, so this is omega n. So, omega r will becomes r pi by L into root over t by rho. So, I am using rho. So, this omega r square term you can write equal to n square pi n square r square by L square into t by rho. So, already we have t by rho, and this is pi square r square by L square. So, this thing can be written as omega r square. So, I can write this integration equal to omega r square delta r s. So, when r equal to s, this integral will reduce to omega r square delta omega r square, and when r not equal to s, this value will become 0. So, we have seen the mode shapes are orthogonal, and from this also we have checked that this integration 0 to L rho phi r x phi s x, where phi r and phi s are rth mode shape and s mode shape. So, this is equal to delta r s when r s equal to 1, 2. So, you can take any number of modes. So, this delta r s is the Kronecker delta, and also we have proved that 0 to L this omega or t d phi r x by dx into d phi s x by dx equal to omega r square delta r s. So, in this way you can find or you can show that different modes are orthogonal to each other, and so you can, using this property of orthogonality, you can find the free vibration response of the system. So, a general free vibration response of the system, that is u x t, will be the summation of all the modal frequencies, or you can find this u x t from the contribution of different modes, and you can write this u x t as summation I equal to 1 to infinity phi n x into q n t. So, this equation can also be written like this. So, already you have seen for a string this is equal to, so this is equal to I equal to 1 to infinity. So, this is equal to b I, so for phi x I can write b I sin n pi x by L, and for q n I can write this is equal to C1 I cos omega t plus C2 I sin omega t. So, I can multiply this b with this c, and these 3 constants can be reduced to 2 constants, and so I can write this expression for the free vibration response of the system like this. So, this will be equal to I equal to 1 to infinity. I can write this as a I, or let me write in terms of same c. So, some other c term or d term I can use. So, this becomes d I cos d1 I cos omega t omega I t plus d2 I sin omega I t. So, where this omega I are the natural frequencies of the system. So, this into, so this into this mode shapes term also will be there. So, this into sin n pi x by L. So, already you know the relation between this omega and omega for different mode shapes, different modes. So, for different modes you have seen this omega equal to, already you have found the expression for omega for this transverse vibration of the string, and this can be written in this form. So, omega n equal to n pi by L root over T by rho. So, this is for the nth mode, and the final expression for this, for the case of the string, you can write in this form. So, u x t equal to d1 I cos omega I t plus d2 I sin omega I t into sin n pi x by L. Now, let us find the mode shapes for the case of the longitudinal vibration of rod. So, in this case we will take different boundary conditions and we will find the frequency equation and the mode shapes of the system. So, let us take the case of a free beam. So, in case of the free rod, so this is the free rod. So, in this case both the ends are free. So, when both ends are free, these ends are not stressed. So, there is no stress in this, in these ends, as there is no stress in the ends. So, I can write that the stress term, stress equal to E del u by del x equal to 0, as del u by del x equal to 0. So, I can write E del u by del x, that is the stress sigma equal to 0. So, I can write this del u by del x, that is the strain equal to 0 at both the ends. So, this u you can write in this form, u equal to phi x into q t. So, as u equal to phi x into q t, and this expression is valid for all the time these boundary conditions, that is del u by del x equal to 0 at the free end and at the probe, at both the free end are 0, at the slopes this del u by del x equal to 0 at both the ends for all time. So, you can write this phi x at x equal to 0 or del phi x by del x at x equal to 0 equal to 0. Similarly, del phi x by del x at x equal to L also equal to 0. So, as phi x you can already got the expression for phi x, that is equal to a cos omega by c x plus b sin omega by c x. So, you can find this d phi x by dx. So, that is equal to A into omega by C. So, this becomes, if you differentiate this thing, this becomes sin omega by C x minus plus B into omega by C cos omega by C x. So, when x equal to 0, so for x equal to 0, d phi x by dx equal to 0, d phi x by dx equal to 0. So, this implies that this b into this cos term, b into omega by c, a omega by c into 0, sin 0 equal to 0. So, this becomes equal to 0. So, this implies this b term equal to 0. So, from these boundary conditions you have seen that this b equal to 0. So, as b equal to 0, so your phi x now becomes phi x equal to a cos omega by c x. So, now d phi by dx at the right end, d phi x by dx at the right end, that is x equal to L, can be written as, so this becomes a omega by c into a omega by c sin omega by c x. So, this is equal to, at x equal to L equal to 0. So, I can write this as a into omega by c sin omega by c L equal to 0, or I can write this as a sin omega by c L equal to 0. So, from this, as a cannot be 0, because when a equal to 0 you will have a trivial state solution, that means there will be no vibration of this rod, this may be a rod. So, there will be no vibration of this rod. So, you can take this as a free beam. So, in this case, or you can take this as a free rod. So, in this both the ends are free, so it is not stressed. So, as this is not stressed, in this case you can find that the stress are 0. So, E into strain will be equal to 0, or strain will be equal to 0, that is del u by del x will be equal to 0. And as you know, this u can be written in terms of phi x and qt. So, for all times to come, strain at these two ends will be equal to 0. So, for that reason, so you can find this expression of the mode shape like this, a sin omega c by L equal to 0. If I am making this a equal to 0, then there will be no vibration of this rod. So, for this free rod there will be no vibration when a will be equal to 0, but as the rod is vibrating, we are studying the vibration of this rod. So, a cannot be equal to 0. So, as a will not be equal to 0, so in that case I can write this sin omega by, so this is omega sin omega by c L will be equal to 0 equal to sin n pi by L. So, as this is equal to sin n pi by L, so I can write this omega L by, so omega L by c equal to n pi, or you can write this omega equal to n pi by L into n pi by L into c. So, this is equal to, so in case of this rod, this is can be written the c equal to E by rho. So, where E is the Young's modulus and rho is the mass per unit length of this rod. So, in this rod the mass per unit length I am taking equal to rho, and E is the Young's modulus. So, in this case when it is vibrating, that time the frequency of the nth mode you can write in this form. So, this is equal to n pi by L into E by rho, and the mode shape you can write, or eigenfunction you can write in this form. So, the eigenfunction will become a sin, so phi becomes, so as a not equal to 0. So, this phi x be equal to 0, you can write phi x equal to a cos omega by c x. So, phi equal to a cos omega by c x, and for omega I can substitute this value equal to n pi by L into root over E by rho. So, this omega by c can be written, or this omega by c equal to n pi by L. So, this expression for phi equal to a n, for phi n can be written a n cos n pi by L x, cos n pi by L x. So, you can see that this free rod vibrates in a cosine, as a cosine form. So, in this rod the vibration will takes place. So, in this case the vibration will takes place in this longitudinal direction. So, in this longitudinal direction the wave propagation will takes place in a cosine way. So, this phi n equal to a n cos n pi L by x. So, you can write this first modal frequency equal to pi by L into E by rho, and second modal frequency will be equal to 2 pi by L into root over E by rho, and similarly the nth modal frequency will be n pi by L into root over E by rho. That means, the nth modal frequency is n times the first modal frequency of the system. So, the general vibration or the free vibration response of the system, you can write this u x t will be equal to summation. So, this will be equal to summation, like in the previous case of string I can write this as d1 I equal to 1 to infinity. So, d1 I cos omega I t plus d2 I sin omega I t into, so in this case it becomes cos. So, it will be cos n pi x by cos n pi x by L, or so this is equal to omega n by x by L is your, so for n I can substitute this equal to I. So, I pi x by L. So, u x t, that is the free vibration response of the system, becomes I equal to 1 to infinity d1 I cos omega I t plus d2 I sin omega I t into cos I pi x by L. So, in this d1 I and d2 I are the modal participation of the ith mode. So, these two, this d1 I and d2 I, you can obtain it from the initial conditions of the system. So, let us find the mode shapes for the case of a clamped free beam. So, let one end is clamped and other end is free. So, this end is clamped and other end is free. So, in this case we have to find the mode shapes of the longitudinal vibration of the rod. So, in case of a clamped free beam, clamped free, so this is a clamped free rod. So, we are interested to find the longitudinal vibration of this rod. So, in this case the boundary conditions are, so at the fixed end displacement will be equal to 0, and at the free end the stress will be equal to 0. So, at the stress equal to 0, already we have seen that it can be written at the free end d phi by dx equal to 0, and at the fixed end phi x equal to 0. So, our boundary conditions will be phi 0 equal to 0 and d phi by dx at x equal to L will be equal to 0. So, we can write this phi x in this form. So, phi x will be equal to a cos omega by c x plus b sin omega by c x. So, in this case I can substitute this phi x equal to phi 0 equal to 0. So, that will give b equal to b into 0 plus a equal to 0 or a equal to 0. So, that will give a equal to 0. Phi 0 equal to 0 implies a equal to 0. So, now differentiating it once. So, I can write this d phi by dx, d phi by dx becomes a omega. So, now the remaining term as a equal to 0. So, we will have phi x equal to b sin omega by c x. So, we have phi x equal to, so I can write this phi x equal to, so phi x equal to b sin omega by c x. So, d phi x by dx. So, d phi x by dx will be equal to b omega by c cos omega by c x. So, now at x equal to L this equal to 0. So, this implies that this b cos omega by c L equal to 0. So, today class we have studied the free vibration response of string and also for the longitudinal vibration of the rod. For the case of string, we have shown that the eigen functions are orthogonal, and for the case of fixed string, we have found the frequency equation and the mode shapes, and also for this longitudinal vibration of rod, we have found the frequency for the case of a free rod. Next class we are going to study about the mode shapes of torsional vibration of rods, and we will summarize the free vibration of continuous systems.